All right, thanks for coming to reInvent, and thanks for coming out to listen to this session today. We'll do a quick round of introductions and then get started with the presentation. I'm Vibhav Vishwanathan. I'm a senior product manager with Amazon EC2, the Elastic Cloud Compute team.
Thanks, Vibhav. I'm Gadi Hoot. I'm running business development and product marketing for Annapurna Labs.
Hi, I'm Adam. I'm a software developer in Alexa text-to-speech team.
Yeah, Adam's here to share customer story of Alexa running on EC2 Instances and their experience as a customer. We'll get to that, the agenda and so on shortly. So we'll start off with an overview of machine learning at AWS. And then Gadi will give an overview of AWS Inferentia, the software and hardware parts. I'll take the mic back to talk about the EC2 Instances, and then the customer story, Adam will take over. And then we'll end with a Q&A. I'll answer the easy questions. They're here to answer the harder ones. All right. OK, so customers across a diverse set of industries, from retail to real estate, are using machine learning to define new categories and experiences. Most of this machine learning today is done on AWS. We have tens and thousands of customers with twice as many references or customers than any other cloud provider. It's a broad and fast-growing group. You can see the customers here, including Airbnb, Slack, Pinterest, Convoy, and so on. All the amazing quality of the Tinder matches that you might have got, it's thanks to the machine learning that's been running on AWS. All right, this is an important slide. As machine learning applications are growing in sophistication and becoming more expensive to run in production, there's been a lot of focus on the training aspect or the cost to train. But customers have told us that majority of where they see infrastructure costs for machine learning comes actually from inference. So as an example, at Amazon, about 90% of the machine learning infrastructure cost comes from machine learning inference. So if you take Alexa as an example, the model is trained maybe once or twice a week. But there are so many calls that we make. Every query or every question you ask Alexa, she has to run an inference to get you the answer. So we took this feedback and we wanted to build something that is high performance, low cost. So we built a product from the ground up that tackles the high cost of deploying machine learning inference in production. We built our own chip, which is AWS Inferentia. With that, I'll hand over to Gadi.
Thank you. OK, so let's dive right into it, talk about AWS Inferentia. Let's start with the chip itself. When we started thinking about designing this chip, we wanted it to be high throughput, low power, and low latency, and easy to use. That was a key metric for us to make sure customers can actually use the dedicated hardware. It was designed to allow customers for maximum throughput while maintaining real-time latency. Each Inferentia device hosts 4 neuron cores. In each neuron core, we implement in hardware a high-performance systolic array matrix multiply engine, which happens to be really efficient in processing deep neural networks. Each neuron core also has a two-stage memory hierarchy, a large on-chip cache, and commodity DRAM attached to each of the chips. It's built for maximum customer flexibility and allows for multiple data types to be processed: int 8, floating point 16, bfloat 16. And also there are ways to process floating point 32. We'll talk about that later. And it can be used from all popular machine learning networks, including PyTorch, TensorFlow, and MXNet. Another important aspect of the chip is a fast interconnect that is implemented. All the chips in an instance, if the instance has more than one chip, are interconnected to each other. And this is key to some functionality that we'll discuss soon. As I said, it's natively integrated to the frameworks, and most, if not all, customers will not have to change their models, and will not have to. They will have to change only a few lines of code on the framework level to get started with Inferentia. So ideally, you train your model on a P3 or P3DN in EC2. You bring the trained models to Inferentia, change a few lines of code in the framework, and you're starting to use Inferentia. Many of our customers also challenged us to push latency down as much as possible. This is extremely important for applications that are user-facing and interactive in nature, where end users expect results fast, and those applications typically are bounded by the maximum latency that they can tolerate. The problem is that as machine learning gets more sophisticated, the models grow in size, and you spend a lot of time in moving models in and out of memory. So that adds to the overall application latency and makes the compute problem larger. So Inferentia has a unique capability to deal with that situation, and we can take a model, shard it to multiple chips, put all the model inside the on-chip cache, and then stream the data in a pipeline fashion through those chips using the fast interconnect. What this does is it cuts the latency. For example, for BERT, it cuts the latency for up to 2/3 compared to not using that mode. And you also keep the same throughput. So that's really important for real-time applications that require fast response. So that's on the hardware. But dedicated hardware is, you need something to interface to that hardware and make sure it's easy to use. And I'm happy to announce and introduce to you to AWS Neuron. AWS Neuron is the SDK enabling high-performance inference on Inferentia. It's designed from the ground up to allow for maximum flexibility, optimizing for highest throughput and low latency in a variety of use cases. It comes pre-integrated with the popular frameworks I already mentioned, and supports commonly used machine learning models such as ResNet for image recognition and BERT for natural language understanding. And you can start using it immediately using the AWS DL AMI, and with DL containers, ECS, EKS, and SageMaker support coming soon. Let's talk a bit about the components of Neuron. We have three main components. The first one is the compiler, where you take your trained model and compile it for the hardware. Second one is the runtime component that you use in order to push models down to the chips and get the inference running. And of course, we also need to have some profiling tools to help you tune your models if you feel like your application needs to be tuned to certain parameters. With Neuron, you can develop, deploy, and run the high-performance inference application using state-of-the-art neural networks at scale. With existing models running in one of the supported frameworks, as I said, in most cases, you will not have to change only a few lines of code. And you can integrate AWS Neuron to an existing framework that you're already using. Or if you have a customer environment, you can use a pip-will install, standard pip-will install to take Neuron to your own environment, your own AMI. You can even work without a framework at all, if that makes sense to your application. So it's very flexible in how developers can integrate that into their application. Now let's talk a bit about a few of the highlights of Neuron. The first one for ease of use is smart partitioning. Smart partitioning helps you to optimize the neural net compute components and using the ahead-of-time compiler. And it's able to partition the neural network optimally and intelligently and recommend you the optimal instance size to use for your specific model. The compiler also, when compilation finishes, the compiler also gives you predictions on what will be the latency of your model running on Inferentia, on those instance sizes, and what is the expected throughput. So it helps you, even before running on Inferentia, tune your model and see if you're in the right direction. Second capability, we heard from many developers that we call FP32 autocasting. We heard from many developers that although training for floating point, 32-bit floating point is time consuming, the advantage is that it gives the best accuracy. But it's really hard to move a 32-bit model to a 16-bit environment to enjoy the performance benefits. So Neuron and Inferentia are the first accelerators in AWS that can take a 32-bit trained model and automatically convert it to 16-bit, either bfloat or FP16. So as a user, you don't really need to do anything. You just tell give the compiler a 32-bit model, and it's automatically converted to 16-bit. The third capability is Neuron Core Pipeline. So Neuron, if you remember the slide I talked about the pipeline manner, so you can tell Neuron, this is the mode I want to work. I want to work in a Neuron Core Pipeline mode. And the compiler will take your model, split it between the chips on the instance, and run and expose itself to the runtime as one large neuron device. And to the framework, this is completely transparent. The framework sees one device, one neuron device, while in hardware we pipeline all the inferences to gain the latency benefits. Last component, a unique capability of Neuron is Neuron Core Groups. If you remember, each chip has 4 neuron cores. If you run large instance sizes, you can get up to 64 neuron cores. And as you'll hear from Alexa later, there are ways to take those cores and allocate them for specific models. So you can run concurrently different models. You can do that in batch or real time. And by that, optimize the utilization of your hardware as much as possible. This is especially good for applications that require different neural nets, for example, decoding and encoding text-to-speech, which you'll hear about from Alexa. The second component of Neuron is the runtime. Runtime can run as a container environment or can run natively. It's a user space application that provides developers with the flexibility to deploy the inference application and optimize for high throughput. It takes the compiled model, loads that to the Inferentia chips with standard the same standard interfaces you will load the model in a framework today. The container version is available over the ECR repositories and can be used directly, or you can install Neuron, like I said before, with pip install Neuron Runtime into your own environment. Our GitHub contains examples of how to deploy, and more deployment options coming soon, as I said before, with ECS, EKS, and SageMaker. The last Neuron component is the profiling tools. Profiling tools include utilities to help you increase visibility into actual inference and fine-tune your model and your execution pipeline. It includes a Neuron TensorBoard plugin that provides useful information related to the Neuron devices, such as compatibility and profiling information. It also preserves the TensorBoard's debugger plugin, which may be useful in finding numerical mismatches. So that's the quick tour of Neuron. Neuron, together with Inferentia, can help you accelerate your model processing. I'll pass it back to Viba. We'll show you actual examples and how we deploy that into instances.
Thanks, Gadi. All right, so let's come back to Amazon EC2 Instances. Right. So I'm excited to announce this. We announced this yesterday in Andy's Jassie's keynote. Instances are optimized to run ML inference workloads, and they serve a variety of use cases. Right, so you can run high-scale ML inference workloads for object detection, NLP, personalization, speech recognition, image processing, fraud detection, and so on, to name a few. But it spans, obviously, a wider range of use cases for ML inference. Our internal Alexa team, their TTS, or text-to-speech team, their use case to run inference on Inf1 instances is their text-to-speech service. Adam will talk more about that towards the later half of the presentation. So this, as Gadi spoke about, like, it's got multiple different parts, and they've been built from the ground up by AWS. So, on the left side of the slide, you see the AWS Inferentia and the Neuron stack that Gadi spoke about. It's built on the AWS Nitro system with our custom Intel processors. Now this together gives you high performance at a low cost. Now there are a few deployment options within Amazon EC2, and I'll just run through how you should think about choosing amongst the portfolio of instances for ML inference. So on the left, you have EC2 Inf1 instances, right? These are powered by AWS Inferentia and Neuron. Applications that leverage common ML frameworks such as TensorFlow, MXNet, and PyTorch, we recommend that you use Inf1 instances. Today, they are best price to performance for ML inferencing in the cloud. They're up to about 40% lower price per inference compared to our G4 instances. Now, our G4 instances, prior to the announcement of Inf1 instances, were provided the best cost per inference in the cloud. We recommend using G4 instances if your applications are heavily dependent on any of the NVIDIA libraries, such as CUDA or cuDNN libraries. They are based on NVIDIA's T4 GPUs. And on the right, you see EC2 C5 instances. These are powered by our Intel Skylake and Cascade Lake processors, which has got the DL Boost instruction set. We recommend that you use the C5 or the CPU instances if your applications have low sensitivity to inference performance. Now this slide gives you the specifications of the Inf1 instances, right? So it comes in 4 different sizes, from X large to 24X large. They have 1:2 vCPU to memory ratio, right from 4 vCPUs to 96 vCPUs. The XL and 2XL are single chip variants of the Inferentia chip, whereas the 6XL and 24XL have 4 and 16 respectively. They will also, you can enable the Neuron Core Pipeline mode in those. They will be soon available to use with some of our managed services such as SageMaker, ECS, and EKS. So we ran some, sorry.
What about batch? Is AWS batch?
Yes, it will include batch as well. All right, so the metrics that obviously that matter the most for ML inference is throughput and latency, some of which Gadi spoke about. So we ran the BERT-based model. We are excited to show you some of our internal benchmark numbers that we ran. This was an end-to-end performance test. We chose the largest Inf1 instance size and compared to the largest G4 instance size. And as you can see on the slide, Inf1 instances offer up to 3x higher throughput and up to 40% lower cost per inference compared to EC2 G4 instances. From the table, you can see that the throughput on Inf1 was 19,200 sequences per second, while for G4 it was 5,800-ish sequences per second. Today, Inf1 will give you the highest price to performance in the cloud for ML inference. So just coming back to availability, they're available in US East 1 and US West 2 today. That's our North Virginia and Oregon regions. The more regions are being added soon. We'll have a broader global rollout next year, so you'll be able to access across the world pretty shortly. They're available in the standard EC2 purchase options, such as on-demand, reserved instances, and spot. We are also enabling it as part of savings plan, which is something that we recently announced as a price offering. The 1-year and 3-year RIs, for those who are not familiar, it's a 1-year and 3-year capacity reservation that you could make on the instance. With that, you get a 40% and 60% discount off of the on-demand price. The smallest size XL starts at $0.368 per hour.
Question.
Yeah.
Do you know when it's going to come to GovCloud?
GovCloud would be early 2020. Yeah, that's the that would happen as part of the broader global rollout. All right, with that, Adam, I'll pass the mic to Adam to talk about
Thank you,
Alexa.
Bob. Okay, so let me share with you the customer story, how newly released Inferentia helped Alexa text-to-speech to reduce their cost of fleet.
Guys, something happened there?
I think I pressed the wrong button.
You pressed the wrong button? Okay. Okay, so we're restarting now. Yeah, okay. Good to go.
Thank you. So before going into the details of how we manage to cut our costs, let me start with briefly introducing where Alexa text-to-speech sits within Alexa stack. So Alexa, as a complex dialogue system, consists of multiple components, many of which employ machine learning models. So let me start with going across the major components, walking along with the customer request. So once the customer starts speaking to the device, the first thing that happens is the wake word recognition, which spots the Alexa word, and from that point on, it starts recording the speech of the customer and streaming it to the Alexa cloud service. From that point on, the rest of the processing of the customer query happens within the cloud, not on the device. So Alexa Cloud Service is the orchestrator of the processing. The first thing that needs to happen, we need to recognize what was being said by the customer. For that to happen, Alexa Cloud Service is sending the audio stream to the automatic speech recognition system. This system, the service is handling, recognizing what is the sequence of words that was spoken by the customer. This is being sent back to the Alexa Cloud Service, and the next task that we need to do is to understand what is the customer intent behind these words. This is done by the natural understanding component, which receives the sequence of words, and it needs to recognize what is the intent, plus what are the attributes of this intent. This means that we need to learn whether the customer requested to play a song, or to learn about whether in some location, plus we need to learn what is the song he wants to play, or what is the location he's interested about. Once this is done, Alexa Cloud Service searches for the right Alexa skill within the Alexa ecosystem that is able to handle that request. The intent data is sent to the skill, and the skill has the implementation of the logic that handles the request. Once this is done, the skill might send the play directive to the Alexa Cloud Service, which means that some spoken response is expected to be played back on the Alexa device. Synthesis of the text within the play directive is handled by text-to-speech service, which receives the text and generates the spoken form as the audio stream, which is being sent back to the device. So from that point on, let's try to dive deep how the Alexa text-to-speech system works. So it contains two major machine learning components. The first is named as context generation, and the second is speech production, also named as neural vocoder. So context generation is receiving the input, the textual input in the form of the linguistic representation. That means that what we receive to the first model is a sequence of sounds that are expected to be pronounced. It converts this sequence into intermediate acoustic representation that is formed as about 80 vectors per each second of speech that is going to be generated. Context generation is handling sequence to sequence, as both sequences have different and variable lengths. We use encoder-decoder model for this purpose, and the output is presenting properties of the audio that will be generated, including what are the words that will be spoken, what is the style, what are the properties of all the properties of the audio. The second model, which is speech production, converts this representation into the actual speech signal. Because we are required to deliver hi-fi quality of the speech signal, it is being represented as in high resolution. That means that we need to generate 24,000 outputs per each second of speech. So knowing now what are the main components, let's talk about what are the challenges to accomplish the task of speech generation. So let me start with telling a few words about the requirements for our system. So as we are part of the Alexa dialogue system, we have pretty strict requirements related to the latency. Human-computer interaction requires not exceeding certain limits, as otherwise this would be perceived by the user as unnatural. As Alexa text-to-speech is only part of the dialogue system, our requirement is in the range of tens of milliseconds. To meet these requirements, we are not processing the request end-to-end before sending the response, but rather than that, we process it in small chunks. Once the first chunk is ready, we are sending this back to the customer, and at the time this chunk is being played back on the device, we are processing the next chunk, and so forth. There is a catch in this process because the audio stream being played cannot underrun the buffer. Otherwise, we will have a strong artifact audible to the customer. This means that the processing of generation of the audio in the system needs to be much faster compared to the playback rate, including all the network latencies and so on. We have a requirement that it needs to be at least 5 times faster. Now, going back to the two major components that I was presenting on the previous slide, we have two models that have significantly different nature. Context generation is a sequence-to-sequence model with autoregressive loop. This type of network has pretty high demand on the memory bandwidth, and it doesn't necessarily have high demand on the compute power because the output rate is only 80 outputs per second. On contrary, the second model of speech generation is operating on very high temporal density, and because of the complex nature of human speech that it is expected to reconstruct, it requires very complex architecture of the network. This results that we require around 90 billion floating point operations to generate each second of speech. As the result, the whole problem of speech production becomes compute bound. In past, to solve the problem of text-to-speech, what we ended up is the service architecture that is running on GPU instances, namely P3 and GeForce. We use two types of instances. P3s are delivering higher throughput and lower latency. However, GeForce are cheaper. Still, the cost of maintaining the fleet is very high, and because of the high number of Alexa customers, and we are looking around for cheaper options, and this brings us to the newly released Inferentia. So let's talk a little bit about what was the effort to migrate Alexa text-to-speech to Inferentia. Alexa text-to-speech is an application implemented in C++ that uses MXNet linked through cpredict API to execute machine learning workloads. Both cpredict API and MXNet are natively supported by AWS Neuron, and as an effect, to build the first proof of concept, we were required just to compile our models and make limited number of changes within the code to integrate against them and run them on Inf1. However, to get best of the new platform, we needed to invest more and experiment with different architectures and solutions. Here comes handy Python API supported by Neuron, because one can easily experiment with different configuration options and in Python before re-implementing them in C++. One of the major risks when integrating against Inferentia was the question whether we are able to deliver the same quality as on GPU. The major vector of this risk was the fact that we were using FP32 weights, while Inferentia is only supporting 16-bit resolution. The good thing was that we had the option to try out two different formats, bfloat16 and FP16, and choose the best quality delivered by both of them. On this slide, I would like to present what is the architecture that we found as the most optimal at this point. Each text-to-speech process that is running is connected to two Inferentia chips. The first chip is dedicated to executing context generation, and the second is dedicated to speech production process. The first Inferentia is running in the neuron core pipeline mode because, as you remember, context generation problem is memory bound. Therefore, we use the pipeline mode so that all the weights fit into the neuron core caches, and we avoid memory bottlenecks. The second Inferentia is working in a neuron core group where we run 4 parallel vocoder processes, each attached to one of the neuron cores. This delivers the highest possible throughput on this Inferentia chip. At the end, we are concatenating the resulting audio streams. To avoid the situation that one of the Inferentia is staying idle, we pipeline the process of context generation and vocoding. After finishing the first context generation chunk, we are starting the vocoding, and at the same time, in parallel, we are generating the audio context for the second chunk. This way, the only time when one of the Inferentia stays idle is in the beginning or at the end of the sentence. So now let me present what are the results and gains that we managed to achieve. So we did number of tests to validate how the new platform compares to the existing baselines. As the baseline, I'm comparing against two GPU platforms, namely P3 and G4. So the first test that we did was based on the Alexa generic traffic, which consists of mostly short sentences. So what we can see here is the fact that Inferentia is delivering the lowest possible cost among the three platforms tested. In detail, we are about 45% lower cost compared to P3 and about 20% lower compared to G4. At the same time, the latency is almost as in match with P3, which is not the case for G4, which produces higher latency.
Question?
Yes?
The cost here is basically instance cost? Because it's
No.
all inside Amazon. So.
Yep. So the cost here is measured. What is the cost of generating 1 hour of output speech?
Okay.
So-
But measured as time to run it on the...
Yeah, so what we are measuring is how much time of the instance I need to spend to generate 1 hour of output speech,
Okay.
and then take into account that each instance has different pricing. And at the end, I get how many dollars I need to spend to generate 1 hour of speech. Thank you for the question.
Yeah, AWS and Alexa are two different entities. We will charge them still. Yeah.
So it's the same public pricing
Yeah.
used for calculation.
Yes. Okay, so let's go to the second test that we did. So as I was mentioning when I discussed the architecture, the process is somehow inefficient in the beginning and end of the each synthesis, because one of the inferentials stays idle. This portion of time is proportionally less to the whole time of the processing when the request that we are processing is longer. Part of the Alexa domains are containing text that are long form, such as books, news articles, and so on. For this, we expect to achieve better cost efficiency on Inferentia. And we did a test to confirm that, and the result of this test is presented within this slide. So what we can see here is that the cost saving compared to GPU instances is about 10% lower compared to the results on the short texts. So here we are 55% lower compared to P3 and about 30% lower compared to G4s. I don't present here what is the latency, because for the book or news generation, latency is not that relevant compared to the dialogue generation. So for us, this is the beginning of our adventure with Inferentia. And the fact is that we spent quite a while on optimizing our solution running on GPUs. While at this point we are having the initial product version on Inferentia. We are anticipating many improvements to come. We see a number of them already, including improvement in the pipelining process that was mentioned, improvements on memory transfers, on reducing memory transfers between the host and Inferentia chips. And when we anticipate what are the gains from that, we should expect to be about half of the price on compared to G4s. And at the same time, we anticipate that the latency will be reduced by 20% compared to P3s. Thank you. So let me go back to Vibav.
Thanks, Adam. All right, that's a wonderful customer story. Thanks. All right, so with that, we conclude the major part of the presentation. I don't think we have.
No, we have mics, so we can open up for questions now. If you guys have any question, a mic will magically arrive to you, and we can start the Q&A part. Going once.
So any timeline regarding that?
No, mic first, because we need it. Everybody needs to hear. Thank you.
Just wondering the time. Just wondering the timeline for the EKS and ECS supporting that coming soon.
Yeah, so this is coming in January 2020.
Sounds good.
Is there a specific use case for the ECS EKS that you have, or?
Yeah, so we are planning to move to Kubernetes, and we also would like to run on GPU. So.
Okay. Okay.
Great. Okay. We can start with questions to see if you remember what we said today. Okay. So if someone wants to ask us a question in private, we are here, so thank you, everybody.
Yeah, thanks for coming. Hope you have a
Thank you.
good rest of your trip.